بسم الله الرحمن الرحيم. سنقوم بعرض المحاضرة 11 والأخيرة بمادة التبريد كورس نمبر 401. تشمل هذه المحاضرة كيفية حساب الأحمال التبريدية لغرف التبريد المركزية. The segments of total refrigeration load are: 1. Transmission load, which heat transferred into the refrigerated space through its surface، وهي الأحمال التي يتم انتقالها من خارج غرف التبريد إلى داخل غرف التبريد عبر الأسطح المواجهة لاختلاف في درجات الحرارة، مثل الحوائط الجانبية والسقف والأرضيات. 2. Product load, which is the heat removed from and produced by products brought into and kept in the refrigerated space. أحمال البضائع أو المنتجات التي يتم تخزينها أثناء عملية التشوين أو أثناء عملية التخزين التي يمكن أن تنتج نتيجة عن التنفس، حمل Respiration Load لبعض المنتجات مثل الخضروات والفواكه التي يتم حفظها في درجات حرارة أعلى من درجة حرارة الصفر. أما المنتجات مثل اللحوم والدواجن والأسماك التي يتم تخزينها في درجة حرارة أقل من الصفر، فيكون حملها أثناء عملية التشوين لتخفيض درجة حرارتها من درجة حرارة التعبئة إلى درجة حرارة الحفظ التي تبقى عندها لمدة قد تصل إلى 6 أشهر أو بحد أقصى سنة أو 18 شهر، طبقا لدرجات الحرارة التي يتم الحفظ عندها وطبقا للجداول المعمول بها في حفظ مثل هذه الأطعمة. 3. Internal loads, which is heat produced by internal sources such as lights, electrical motors, forklifts and people working in the space. الأحمال الداخلية والتي تشمل كافة الأحمال الناشئة من أحمال الإضاءة، المحركات الكهربائية الخاصة بمراوح المبخرات، أحمال أوناش التحميل من النوع الفوركليفت، وأحمال الأفراد الحرارة التي تنبعث من أجسامهم أثناء ساعات العمل في الغرف التبريدية. 4. Infiltration Air Load, which is the heat gain associated with air entering the refrigerated space، وهي أحمال الهواء المتسرب من خارج الغرف إلى داخلها عبر الأبواب أثناء عملية التحميل أو التفريغ، وبالتالي يمكن حساب هذه الأحمال بفروق درجات الحرارة الخارجية والداخلية، مع الأخذ في الاعتبار كميات الهواء التي تمر عبر هذه البوابات أثناء عمليات الفتح والغلق في بدء ساعات العمل وفي نهايتها، وطبقا لفروق الكثافات ما بين الهواء الخارجي والهواء المبرد داخل غرف التبريد. 5. Equipment Related Load، أي أحمال قد تنشأ نتيجة للمعدات التي يتم استخدامها داخل غرف التبريد، والتي يمكن أن تشمل بعض الأوناش أو المحركات الكهربائية الخاصة أو المحركات الديزل الخاصة ببعض الروافع، أو أي معدات ميكانيكية أو كهربائية تؤدي إلى انبعاثات داخلية للأحمال الكهربائية تتمثل في صورة حرارية قد تؤثر بالسلب على الأحمال التبريدية الداخلية لغرف التبريد. The first 4 segments of load constitutes the net heat loads for which the refrigeration system is to be provided. The fifth segment consists of heat gains created by refrigeration equipment. Thus, net heat load plus equipment heat load is the total refrigeration load for which a compressor must be selected. This chapter contains the load calculating procedures and data for the first four segments and the load determination recommendation for the fifth segment. Information needed for the refrigeration for specific heat can be found in chapter 14 and chapter 16 through 28. وبالتالي يشمل هذا الباب جميع الأحمال الأربعة الأولى التي تم ذكرها في الشريحة السابقة، بالإضافة إلى آليات حساب المركبة الخامسة لللود وللحمل، وهي التي قد تنشأ من الإكويبمنت التي قد تكون بداخل غرف التبريد طبقا للأحجام المختلفة لهذه الغرف. Firstly, we will go through the first load components, which is transmission load. Transmission load, sensible heat gain through wall, floors, and ceiling is calculated as a steady state as Q equal U A delta T, where Q is the heat gain in watt, A is the outside area of the section to be calculated. Across it, the heat will be transferred in meter square. Delta T is the temperature difference between outside air temperature and the air temperature of the refrigerated space in degrees Celsius. The overall coefficient of heat transfer U of the wall or floor or ceiling can be calculated by using the common equation used for the overall heat transfer coefficient, which is listed number 2, U equal 1 over H I plus X over K plus 1 over H O, where U is the overall heat transfer coefficient in watt per meter square Kelvin, X is the wall thickness, such this wall can be considered the side walls facing north or south or east or west, or the ceiling or the floor. In meter, the thickness will be taken in meter using SI units. K is the thermal conductivity of this wall material in watt per meter Kelvin. HI is the inside surface conductance or the convective heat transfer coefficient for inside surface of this wall under calculation in watt per square meter Kelvin. HO is the outside surface conductance or convective heat transfer coefficient of the external surface of this wall from outside, also in watt per meter square Kelvin. A value of 1.6 for HI and HO is frequently used for still air. Such is can be considered as a natural convection can be happen on the inside surface and the outside surface, just beside the wall from inside and from outside. So 1.6 watt per meter square Kelvin is a common value which may be frequently used for this application. If the outer surface is exposed to 15 mile per hour wind speed, HO can be increased to 6 watt per square meter Kelvin. With thick walls and low conductivity, the resistance X over K makes U so small that 1 over HI and 1 over HO have a little effect and can be omitted from the calculation. So walls are usually made for more than one material. Therefore, the value X over K represents the composite resistance of the material. The U factor for the wall with a flat parallel surface of materials 1, 2 and 3 is given by the following equation. To consider the composite wall overall heat transfer coefficient in watt per square meter Kelvin, U will equal 1 over x1 over k1 plus x2 over k2 plus x3 over k3. The thermal conductivity of several cold storage insulation are listed in tableau 1, which will be presented in next slide. These values decrease with the age due to factors of discussed in chapter 23 of ASHRAE Handbook Fundamentals 2001 and also chapter 25 of the same handbook for fundamentals 2001 of ASHRAE includes more complete tables listing the thermal properties of various building and insulation materials to be used to construct the building of the refrigerated space according to its different dimensions. This slide presents the table 1, which include the thermal conductivity of cold storage insulation materials. The insulation such as polyethylene boards are leaded, expanded, or different insulation materials such as cork board, foam glass, or different degree of polystyrene of expanded R142B or R141B expanded with different thermal conductivity values in watt per meter Kelvin starting from 0.023 up to 0.044 based on the different materials listed in this table, which is commonly used for the wall material as an insulation with very low thermal conductivity to reduce the transmission heat load from outside to inside. However, in the right side of this slide we can find table 2. Table 2 lists minimum insulation thickness of expanded polystyrene, polyiso-natural boards recommended by the refrigeration industry. These thicknesses may be needed to be increased to offset heat gain caused by the building components such as wood and metal studs, webs in concrete masonry, and metal ties that bridge across the insulation and reduce thermal resistance of the wall or roof. Chapter 25 of 2001 ASHRAE Handbook Fundamentals describes how to calculate the heat gain through the walls and roofs with thermal bridges. The metal surfaces of prefabricated or insulated panel have negligible effect on thermal performance and should not be considered in calculating the U factors. So we can find table 2 with a minimum insulation thickness, which is commonly used in northern USA and southern USA based on the storage temperature range starting from 10 to 16, 4 to 10, minus 4 to 4, minus 9 to minus 4, minus 18 to minus 10 to minus 9, minus 26 to minus 18, and finally minus 40 to minus 26. The thickness of expanded insulation materials used can be ranged starting from 50 millimeters up to 125 millimeters on both northern US and southern US, as can be seen in this tableau number 2. So we can generate the value of X over K from this table 1 and table 2. Table 1 presents the K values of different materials, and table 2 presents the commonly used thickness, which can be used in our calculation during estimation the overall heat transfer coefficient U, which is based on X, the wall thickness, and the K, the thermal conductivity of the used material. In most cases, the temperature difference delta T can be adjusted to compensate for solar effect on the heat load if compared with the northern side or northern wall, which is in the upper part of the earth. The sun rays cannot be reaches for this uh, northern wall if compared with east or west or south or flat roof. So this slide will present the allowance of sun effect as shown in Tableau 3. The values given in Table 3 apply over a 24-hour period and are added to the ambient temperature when calculating wall heat gain. Latent heat gain due to moisture transmission through walls, floors, and ceiling for modern refrigerated facilities is negligible. Data in Chapter 25 of the 2001 ASHRAE Handbook Fundamentals may be used to calculate this load if moisture permeable materials are used. Chapter 27 of the 2001 ASHRAE Handbook Fundamentals gives outdoor design temperatures for major cities. Values of 0.4 percentage plus or minus should be used for the refrigerated space. Also, this table or this chapter can be used to consider the outside temperature, design temperature in HVAC application in air conditioning system. But for refrigerated space, we can take the values of 0.4 percentage as a selected value from the shown value in this chapter 27. Additional information on thermal insulation may be found in chapters 23 and 24 of the 2001 ASHRAE Handbook Fundamentals, chapter 29 of the 2001 ASHRAE Handbook Fundamentals discusses load calculation procedure in greater details also. So we can find in the right side of this slide table 3, which indicates the allowance of sun effect for east wall and west wall and south wall and flat roof. The typical surface type are grouped in 3 types: dark colored surface, medium colored surface, and finally light colored surface. For dark colored, slate roofing, tar roofing, black paint are listed, and unpainted wood, brick, red tile, dark cement, red, gray, or green paint are listed under the group of medium colored surface. And finally, we can find white stone such as gravel or light colored cement or white paint listed under the group of light colored surface. Then we can find this temperature additional value if we have our in the refrigerated space the dark colored surface, one of these types. The east wall should be considered additional 5 degree in addition to the temperature listed in the major cities here. For northern uh, wall, we should take into account 5 degree additional for east wall and also for west wall. However, for south wall we have to add only 3 degrees Celsius additional, and for flat roof we had 11. If we have a light colored for east wall and west wall, always they are typically, we must add this value to the northern to during the calculation of east and west wall. But for south we add only 2 degree, and for roof we add 5 degree additional to the northern wall when taking into consideration the area of the roof exposed to the sun rays all of the time. So it should be noted that always this value of flat roof is larger than the east and west, which is are typically always typically, and larger also than the south wall due to some movement. Especially this tableau is shown is taken for the upper part of the earth above the equator, where the northern wall the sun ray couldn't be reached for the northern wall. However, if we design a refrigerated space in the lower part of the earth, lower than the equator, in the lower part of the earth, we will take these amounts, but in addition to the southern wall, especially the northern wall reach will have a sun rays, but south wall it will be have no sun rays reaches to it according to the sun movement around the earth. Then we will switch to the second load components, which is the product load. The primary refrigeration load from products brought into and kept in the refrigerated space are 1. The first part of this load component, the heat that must be removed to reduce the product temperature to the storage temperature. Then, and 2. The heat generated by the products in the storage, mainly fruits and vegetables. The quantity of heat to be removed can be calculated as follows. Step number 1. Heat removed to cool from the initial temperature to some lower temperature above freezing. Q1 will be termed here in Q1, which is equal MC T1 minus T2. C and Q have the same abbreviated subscript number 1 to indicate this is the first load components, which indicates the heat to be removed from the initial temperature to some lower temperature above freezing. If we will go to freezing term, then we will go to the another term below freezing. There are another CP, so we will define another CP to generate Q2 equal the same mass C1 or C2 T1 minus TF as a heat removed from to cool down from the initial temperature to the freezing point of the product. So if we have the product initial temperature will be decreased to temperature above the freezing or at freezing temperature, so we will just change the subscript of T2. Instead of T2 we will use TF, but the same C used for the above freezing specific heat, but this amount Q1, this Q2, one of them can be used also during calculation to consider the cooling down period or amount of heat during the cooling down period, the amount of heat removed during the cooling down period from the initial temperature to the storage temperature. Then if we will go to freeze the product, the heat removed to freeze the product will be considered as a Q3, M the mass of the products multiplying by the HIF, which is the latent heat of fusion of this product, as will be shown in here the abbreviation and the nomenclature list in the right side of this slide. Number 4, we can find heat removed to cool from the freezing point to the final temperature below the freezing point. The third part, when we go to freezing, the third part is the heat removed below the freezing temperature. So Q4 will equal MCP below freezing, which is different than CP of the above freezing listed here above in equation 4 and equation 5. We have to use the new CP, which indicates the specific heat below freezing of these products, and we will use the temperature difference starting from T freezing temperature, which have been ended here in the sensible term, the first sensible term. This is the second sensible term, minus T3, which is the final temperature of the product below freezing. So we can find here or conclude that equation 4 and 5 indicates the sensible heat terms of heat above freezing. Even we will reach to freezing temperature as Q2 or not as Q1 for veggies or fruits, and Q2 can be used for meats or fishes or chicken. And to continue with the freezing terms, the latent heat amount listed here or nomenclatured with subscript number 3, the latent heat term. Then the third term to be added to the freezing products is Q4 to consider the last term of sensible heat to be added. Here we can find this nomenclature where Q1, Q2, Q3, Q4 is the heat removed in kilojoule, M is the mass of the product in kilogram, C1 is the specific heat of the product above freezing in kilojoule per kilogram Kelvin, T1 initial temperature of the product above freezing in degrees Celsius, and T2 is the lower temperature of the product above freezing also, C in degrees Celsius. Tf is the freezing temperature of the products at which can be found in chapter 8, the temperature at which this product is freezing, maybe below 0 degree, maybe -2, -1, -5, according to the chemical composition and the water contents inside these products, especially for fishes, meats, and shrimps and chicken. HIF is the latent heat of fusion product in kilojoule per kilogram. C2 specific heat of the product below freezing in kilojoule per kilogram Kelvin. T3 is the final temperature product which it will be kept below freezing in degrees Celsius. The refrigeration capacity required, so we can find here the refrigeration capacity required for products brought into storage is determined from the time allotted for heat removal and assumes that the product is properly exposed to remove the heat in the time. So the calculation is to express the power to use instead of kilojoule per kilogram Kelvin, we have to generate in kilowatt to estimate this product load in as a power in certain time to be cooled, maybe 1 hour. So we will take in 1 hour. If we will need to freeze this amount in 3 hour, 4 hour, 8 hour, 24 hour, so we will use n as a 24 here, and 3600 equals 60 by 60 second by minute to get it the number of hours. And finally we can use for freezing in freezing tunnel can be used this equation Q2, which is indicates use Tf instead of T2, plus Q3 plus Q4. However, if we use just to chilling to chill the product, not to freeze it above the zero, to keep it above the zero, such as the fruits or dairy products or veggies, we can use only equation number 4. Also, we can consider the time to be cooled down this product if we will use freezing tunnel. However, it's rarely used for the products to be used without refrigeration, without freezing, just chilling. We can use the product load, which will be loaded on the refrigerated equipment inside without need to add a freezing tunnel. Equation 8 only applies to uniform entry of the product into storage. The refrigeration load created by non-uniform loading of warm product may be much greater over the short period. See chapter 14 for information on calculating the cooling load of warm products. Specific heats above the and below freezing for many products are given in table 3 of chapter 8 as listed in the previous slide. A product's latent heat fusion may be estimated by multiplying the water content of the product expressed in a decimal by a latent heat of fusion of the water, which is 334 kilojoule per kilogram. Most of food products freezes in the range of -3 to -0.5 degrees Celsius. When the exact freezing temperature is not known, assume it is -2 degrees Celsius. In the right part of this slide, we can find an example. About 100 kilogram of lean beef is to be cooled from 18 to 4 degrees Celsius, then frozen and cooled to -18 degrees Celsius. The moisture content can be considered as 69.5%. So the latent heat is estimated as 233 kilojoule per kilogram, which is the product of 69.5 by 334. If we have these products, the product of these two values, we can find these values can be considered as a latent heat based on the moisture content listed of this lean beef to be freezed. Estimate the cooling load during this freezing. Specific heat of frozen of beef before freezing is listed in table 3, chapter 8, equal to Cp equal 3.23 kilojoule per kilogram Kelvin, and after freezing less 1.68 kilojoule per kilogram. To cool from 18 to 4 degrees Celsius in a chilled room, 100 kilogram by multiplying by the Cp above freezing, multiplying by the temperature, initial temperature, to minus the temperature to be at which will be start to freeze. So we can get 4520 kilojoule in the first term, which is listed in the previous slide as a Q2. Then we will go to Q4 to cool from 4 to freezing point of in the freezer. The same mass multiplying by the Cp from 4 minus 2, which is equal 1940 kilojoule. So finally the latent heat to be taken into the freezing process, 100 kilogram multiplying by the latent heat considered based on the water content, 233. So we can get 23,300 kilojoule to cool from freezing to storage temperature, the final part. So we can use here he used -2, such he couldn't get the temperature, the exact temperature of freezing, so is considered that the freezing temperature is 2 and continue the second part of Q2 to be added to the first part of Q2 until 4, which is listed here. He continue from 4 to -2 and get this amount in addition to this amount, and get finally immediately the freezing the latent heat during the freezing process, and finally to cool from freezing storage temperature the same 100 kilogram multiplying by the Cp above freezing, which have get from table 3 chapter 8, multiplying by the temperature difference of freezing temperature -2 minus -18, the final temperature of to be kept this lean beef amount. So we can get this amount finally as a Q4 to get the total load of this product load. We can have the sum of these four terms we have estimated in the above lines. So the final amount can be considered as 32,450 kilojoule. Example 3 in chapter 8 show also an alternative calculation method. You can go to check it by yourself for more information. Fresh fruits and vegetables respires and release heat during storage. This heat produced by respiration varies with the product and its temperature. The colder the product, the less heat respiration. Table 9 in Chapter 8 also gives the heat of respiration rates for various products. So for various products we can get all the information of respiration load or respiration rate to estimate the respiration load of these products according to the delta T and its rate of respiration uh, based on the values of various products listed in table 9 in chapter 8. Calculations in example 1 don't cover heat gained from the product contains brought into the refrigerated space when pallets, boxes or other packing materials are significant portion for the total mass introduced. The heat load should be calculated. Equation 4 through equation 8 are used to calculate also the total heat gain. Any moisture removed appears as a latent heat gain. The amount of moisture involved usually provided by end user as a percentage of product mass. So with such information the latent heat component of total heat gain may be determined. Subtracting the latent heat component from the total heat gain determines the sensible heat component. Please take this note that the products of meats, fish, chicken, shrimps, any meats products has no respiration loads. The respiration loads only as mentioned here in this slide for fresh fruits and veggies, not for frozen fruits or veggies. For fresh fruits which will must be kept above zero, above freezing to keep it fresh. So we have to consider the respiration load according to its product and the chemical composition of this product and the surface, the outside surface. All these data you can find in table 3 uh, in chapter 8, which have been uh, one of the reference of this lecture and to be used from the ASHRAE handbook of refrigeration to help you during the refrigeration cooling load and design for cold stores. In this slide we will go through the third part of the internal component. Internal load, electrical equipment. All electrical energy dissipated in the refrigerated space from lights, motors, heaters and other equipments must be included in the internal heat loads. Heat equivalent for electrical motor are listed in the attached table number 4 for heat gain from typical electrical motor based on the motor kilowatt and motor type, even split phase or shaded pole or three phase, and according to its nominal RPM and full load of the motor efficiency, the full load efficiency, and according to the different type of motor in driven equipment, motor out of driven equipment, motor in driven equipment, out in what you can get the heat dissipation according to the location of the motor and driven equipment with respect to conditioned space or airstream. You can select the class A or class B or class C, and according to the motor capacity, motor rated in kilowatt, and motor type and motor RPM and motor efficiency. Are different efficiency for each motor class or capacity. You can get the heat dissipation and the heat gain in watt. Then you can transform it to be transformed to kilowatt before inserted to the calculation of the internal load components. Then second part, forklifts. Forklifts in some facilities can be a large and variable contributor to the load. While many forklifts may be in a space at one time, they don't all operate at the same energy level. For example, the energy used by the forklift while it's elevating or lowering forks is different than when it's moving, so it should consider during the internal load components the number of the forklifts and its capacity, and the heat generated from its engine, especially when using diesel engine to this machine of forklift. You should estimate from the manufacturer of this forklift how the amount of the heat dissipated by radiation from this engine of diesel engine equipped the forklift is equipped with. Processing equipment, grinding, mixing, or even cooking equipment may be in the refrigerated areas of food processing plants. Other heat sources included equipment for packing, glue melting, or shrink warping. Another possible load is the makeup air for the equipment that exhausts air from the refrigerated space. All these load components should be considered: electrical equipment, forklift, processing equipment, and also the people loads listed here in this slide. We can find the people load. People add to the heat load, and this load varies depending on such factors as the room temperature, type of work being done, type of clothing worn, and the size of the person. Heat load from a person, QP, subscript P, may be estimated as QP equal 272 minus 6T, small t, where T is the temperature of the refrigerated space in degrees Celsius. Table 5, which is attached to this slide, shows the average load from people in refrigerated space as calculated from equation 9 can be used. These values of heat gains according to the refrigerated space temperature. You can consider the amount of heat equivalent per person according to the number of person. You can multiply each person. So for example, if we have a temperature, a refrigerated space at 0 degree, so and we have 10 person inside this refrigerated space, so each person generate heat equivalent according to this temperature 270 watt per person multiplying by 10, so we will have 2700 watt as a heat generated per of people working inside this cold store. So finally, when people at the first enter the storage, they bring an additional surface heat as a result. When many people enter and leave every few minutes, the load is greater than that listed in table 5 and must be adjusted. A conservation adjustment would be multiplied by the values calculated in equation 9 by multiplying 125 additional, where the conservation of adjustment to be taken during the movement of the people from in and outside the refrigerated space. Also, the latent amount heat component of the internal load is usually very small compared to the total refrigeration load and is customarily regarded as all sensible load in the total load summary. However, the latent heat component should be calculated where water is involved in processing or cleaning. This slide will discuss the infiltration air load, which is the fourth component of internal loads from outside to inside, as can be seen in figure 1, showing the cold air, how the cold air can be exfiltrated from the cold store and how the warm air replacing it from the upper side and enter or infiltrated the refrigerated space or the freezer due to the temperature difference and the relative density difference between the inside air inside the refrigerated space and the outside. So it's recommended to use an air interlock area between the refrigerated space and the outside, the loading dock, which is uh, may include hotter air than the colder air inside the refrigerated space, especially for freezing. And we can see the fog in the lower part due to the cold outflow air in the door opening, at the door opening, so it can generate a fog of air or moist content due to this heavier air compared with the air outside. And on the other side, on the upper side, the warm air inflow inside or infiltrated inside the refrigerated space and can be generated a lot of disturbance inside the refrigerated space and additional internal load due to this door opening during evacuation and filling of this refrigerated space. So heat gain from infiltration air is and associated equipment loads can amount to more than half the total refrigeration load of distribution warehouses and similar applications. So it should be considered carefully. Infiltration air, infiltration by air change or air exchanges happen due to door opening in periodic times during the day, in the operating hours. Infiltration most commonly occurs because of air density differences between the rooms, as shown in figure 1 and figure 2. For typical case where the air mass flowing in equals to the air mass flowing out minus the condensed moisture, the room must be sealed except at the opening in question. If the cold room is not sealed, air may flow directly throughout the door, discussed in the following section. Heat gain through doorways from air exchange is as follows: QT, which indicates the average heat gain for the 24-hour or other period in kilowatt, as shown in equation 10, can be estimated as a equal Q, which is sensible and latent refrigeration load for fully established flow in kilowatt, multiplying by dt, and df, which is dt is the doorway open time factor, or we can name it the duty of opening or opening time, and df is the doorway flow factor. So these two factors are essentially to estimate this value of the heat amount as a function of the sensible and latent heat refrigeration load of fully established flow, multiplying by 1 minus E, which however equal where E equal effectiveness of the doorway protective device if use air curtain or uh, any uh, curtain type of plastic slides, or any way, another way to prevent the air movement from inside to outside or to outside from outside to inside the refrigerated space. علماء in 1975 developed the following air exchange equation for, and it has been established and listed up to date in ASHRI Handbook of Refrigeration, chapter 12. In this equation number 11, Dr. Hani Ulama has listed this equation during his PhD in UK. The equation gives Q equal 0.221 A area, doorway area, multiplying by delta H, HI minus HR. The HI is the enthalpy of infiltration air in kilojoule per kilogram, and the HR is the enthalpy of refrigerated air, of the inside air, in kilojoule also, kilojoule per kilogram, and multiplying by rho r, density of refrigerated air in kilogram per meter cube, multiplying by 1 minus rho I over rho r, where rho I is the density on infiltration air in kilogram per meter cube to the power point half, and finally multiplying by G by H, where G is the gravitational constant 9.81 meter per second square, and H is the doorway height in meter, and finally the density factor Fm, which can be considered in the attached equation number 12, also generated by Dr. Hani Ulama. Fm equal 2 over 1 plus rho r over rho I to the power 1 over 3, and all to the power 1.5. So it should be clear that it is an sophisticated problem to estimate this amount exactly based on the enthalpy and density of both infiltration air and refrigerated air, and doorway area and doorway height, and the density factor. The difference between the factor indicates the difference between the two densities, and we can finally get the sensible heat load and latent heat load refrigeration, which is nomenclatured here in this slide as a Q in kilowatt, to be used in the previous equation number 10 listed in the previous slide to estimate the Q due to infiltration air. Equation 13 also can be used, with figure 3 is a simplification of equation 11. To simplify the equation 11, we can use equation 13, which gives Q equal 0.577 W by H to the power 1.5 multiplying by QS over A, which is the sensible heat load of infiltration air per unit square meter of doorway openings as read. So it's grouped the QS, the sensible, with the doorway in kilowatt per meter square, and finally multiplying by 1 over RS, which is the sensible heat ratio of infiltration air heat gain, which can be taken from tables 6 attached to this slide, or table 7 attached to the next slide, or from stoichiometric chart, which can be used for AC applications to detect the amount of specific heat ratio or sensible heat ratio for a based on the temperature of dry bulb and wet bulb and the relative humidity inside the cold space, which is commonly taken as a 90% relative humidity. So the wet bulb commonly near the dry bulb, such the relative humidity is about 90% relative humidity. So it should be clear that this equation is simplified equation rather than equation listed in the previous slide equation number 11. The value of RS in table 6 and table 7 are based on 90% relative humidity in cold room. A small error occurs where these values are used for 80 or 100% relative humidity. This error, together with loss of accuracy due to simplification, results in a minimum error of equation 13 of approximately 4% regarding to the base equation, which is numbered here in this lecture and chapter 12 as equation number 11, which have been generated since 1975 by Dr. Hani Ulama. Here we can find the continue of the previous slide, table number 7, which have been discussed in the previous slide, and now we will go to the safety factor, and the basis of taking safety factor during the design stage. Generally, the calculated load is increased by a factor of 10% to allow for possible discrepancies between the design criteria and actual operation. This factor should be selected in consultation with the facility user and should be applied individually to the first four heat load components or segments which have been discussed: transmission load and internal load, infiltration load, and product load. Additional 10%. A separate factor should be added to the coil defrosting portion of the equipment load for freezer application only that use dry surface refrigeration coils. However, little data are available to predict heat gain from coil defrosting. For this reason, the experience existing similar facilities should be sought to obtain an appropriate defrost safety factor. Similar facilities should have similar room sensible heat ratios. The nature of frost's accumulation on the cooling coils also affects the performance of the cooling coils units, which isolate the cooling coil from the air to be refrigerated, the return air to be supplied. So, therefore, the refrigeration load, a very low density frost forms under certain conditions, particularly where the room sensible heat ratio is more than a few points below 1. This type of frost is difficult to remove and tends to block the airflow through the cooling coils more readily. Removing this type of frost requires more frequent and longer periods of defrosting of the cooling units, which increases the refrigeration load due to multiplying the, the difference between the operating hour and the total hour of the day, which is 24 divided by 18 hour. For example, if we have 6 hour for defrosting process, so the additional safety factor should be considered the actual time of operating without the frosting, plus regarding to the total hour of the 24 hour, which is the load is calculated based on the 24 hour as mentioned in the previous slides during the transmission load and the product load, and the time to cool down the product. We have to take into consideration this difference between the actual operating hours, which is commonly taken as a 18, and that gives about 6 hours from the 24 hour to uh, make the unit is standby and shut down the equipment and activate the defrosting uh, devices such as electrical heater. So the equipment should be sized to carry out the load of 24 hour in 18 hour by multiplying the final estimation and summation of the cooling load of the first four segments discussed before by 24 divided by 18 hour in this case. Equipment related load is the fifth load component, which should be considered specifically according to the equipment which the refrigerator is equipped with. Heat gain associated with the operation for refrigeration equipment consists essentially of the following: fan motor heater, fan motor heat where forced air circulation is used, reheat where humidity control is a part of the cooling, heat from defrosting where the refrigeration coil operates at temperature below freezing and must be defrosted periodically regardless the room temperature. So all these three terms should be considered as equipment related load and to be added carefully in the four first segments studied and discussed in the previous slides before added to the total load of the refrigeration space. Fan motor heat must be computed based on the actual electrical energy consumed during operation. The fan motor is mounted in the airstream on many cooling units with propeller fans because the cold air extends the power range of the motor. For example, a standard motor in a minus 23 degrees Celsius freezer operates satisfactorily at a 25% overload to the rated nameplate power. The heat gain from the fan motor should be based on the actual runtime, which discussed in the previous slide. Generally, fans on cooling units are operated continuously except during the defrost period, which taken or considered as a 6 hour from the 24 hour, but increasingly fans are being cycled on and off to control temperature and save energy. Cool in 1989 characterized and quantified the heat load associated with defrosting using hot gas. And sometimes we can use defrosting by hot gas bypass from the discharge of the compressor, which is the highest temperature. We can re-inject it in the enter of the evaporator to make it hotter, and then the frost is melting on this coil instead of using electrical heater as additional external load. By using the hot gas of the refrigerant discharged from the temperature at discharge temperature of the compressor. Other common defrost methods use electricity or water. Generally, the heat gain from a cooling unit with electrical defrost is greater than the same unit with hot gas defrost. The heat gain from the unit with water defrost is even less. The moisture that evaporates into the space during the defrost cycle must also be added to refrigeration load. Some of the heat from defrosting is added only to the refrigerant, and the rest is added to the space. To accurately select refrigeration equipment, a distinction should be made between those equipment heat loads and that are the refrigerated space and those are introduced directly to the refrigerating fluid. Equipment heat gain is usually small at space temperature above approximately -1 degree Celsius. Where reheat or other artificial loads are not imposed, total equipment heat gain is about 5% or less of the total load. It should not exceed 5% of the total load of the four segments first segments of the load. However, equipment heat gain becomes a major portion of the total load at freezer temperature. For example, at -30 degrees Celsius, the theoretical contribution of the total refrigeration load due to fan power and coil defrosting alone can exceed, for many cases, 15% of the total cooling load. This percent assumes proper control of defrosting so that the space is not heated excessively. This slide presents example number 2, which is dedicated to calculate the total heat load after we have finished all the load components expected, the four components: the transmission load, the internal loads due to people, lighting, motor, or any equipment, and the infiltration load, and the product load. So for this freezing storage, the design criteria is listed here. The design of summer 33 degrees Celsius dry bulb and 27 degrees Celsius wet bulb. Comments of 0.4% summer and winter conditions can be taken from chapter 25, which is mentioned before. During the transmission load outside temperature consideration in major cities, room dimensions are in meters: 40.5 by 68 by 9 meter in height, length and width and height of the room is listed. The floor area is estimated here as a 2743 meter square. Pallet positions 4800 millimeters. The pallet positions turns per year 20 turns per year, in and out 20 turns 20 times. Use factor 90%. Ambient condition can be listed from table of correction due to east and north and south, and for roof and for floor, to consider the temperature and adding the temperature difference which listed before plus the 33. We can find here that he added for roof the surface temperature 6 degree. Additional sign effects can find 5.5 for floor 0, for wall east 0, and for north and east and west equal 0. So he taking the same temperature. The floor is taking 16, and the west is equal surface temperature -2, and south is equal 7, due to that its adjacent refrigerated meat room is held at -2, and truck dock is held at 7 from east side and from south side, and he take no effect on east or north side, so it takes the same outside temperature as it is. However, adding the additional temperature. The insulation thickness also listed here in this table for different roof and floor and wall materials by listing the different Ks, and then get the use the factors of overall heat transfer coefficient, and finally its inverse, the thermal resistance in meter square Kelvin per watt, are also listed here in this table to help you. Then the heat transmission from each value can be concluded inside this table by taking safety factor 20%. He can get that total transmission load is in kilowatt 66.89 in kilowatt, by multiplying all the delta T by all the area of each wall exposure according to its length, width and height, and its adjacent temperature to get the temperature difference, and finally using the U, and by multiplying A by U by delta T after some getting the product of the area according to the length and width. So one of the lengths or the width multiplying by the height, or for the roof the length and width, the product, the total area 2700. You can see here in this table the load components, and finally the total after adding 20% as a safety factor for this transmission load, taking to consider any additional due to variation of the design away of the design criteria due to the operation and sun effect. Then the product load, he estimates the product load here in this slide by adding the temperature in and temperature out, -15 and -23 is the difference, 8 degrees Celsius, and the specific heat he get at 1.88, and the product, the mass flow, each pallet equal 9845 kilogram per hour. This is the mass flow. He estimates this mass flow according to the rate of the product he can get listed in the heading of this problem, and finally he can get that the product load is equal 82.91 kilowatt. Here he estimated the infiltration load by using the equation of Ulama, which is listed below this tableau. After listing all the door type 1, type 2, type 3. For he has three types: one between the dock and the freezer, one for the dry freezer, and one for meat freezer, which is the two adjacent spaces listed in the this example. So he can get finally all the total loads of each doorway. It should be clear that door type number 1 gives 48.6, the larger amount, and door type 2 and door type 3 gives less amount due to the difference between the temperature is less between the freezer and the meat freezer, and if compared between the dock and the freezers. Finally, the total infiltration load is listed here as 60.45 in kilowatt. The internal loads finally to be estimated: lights, you take lighting level 10.8 watt per square meter according to the floor area 2743 meter square. He can estimate the total lighting load by multiplying and dividing finally over 1000 to get it in kilowatt. He found that the lighting load is 29.62 kilowatt. People load number of 3 person, he assumed 3 person, and the room temperature minus 23. He get the difference, required difference, by the equation listed before for people load, and get the total people load is 1.23 kilowatt. Trucks, he assumed 3 trucks, kilowatt per truck 5.6. So the total kilowatt of these trucks of forklifts inside this refrigerated space is 16.8 kilowatt. All this data is given during the solution or during the hearing or inside the hearing of this problem, can be considered or can be this example for you to show how we can add the different load components as transmission load, infiltration load, internal loads with each component: lights, people, trucks, and fans. Number of fans is 15. Kilowatt per fan equal 1.1 nominal, 1453 watt heat gain per table 4. Finally, he can get the total fan load is equal 21.8 kilowatt, and the load summary can be listed here in this tableau in the right side. Transmission load total from the previous slides 66.89 kilowatt, product load 82.91, motor load is 0, there is no listed about it. The infiltration load 60.45, lighting 29.62, people 1.23, trucks 16.8, fan motors 21.8 from here, subtotal. And finally he take another safety factor for the total, so for about from the subtotal to get the total load in kilowatt as 307.67 kilowatt, the total refrigerated load of this cold store. Load diversity: when computing refrigeration load, the most conservative approach is to calculate each part of the expected peak value. The combined result can overstate the actual total load by as much as 20 to 50%. The reason for such overestimates is that typically that all loads don't occur at the same time of the day. Furthermore, many of them are not always at their maximum value when they do occur. The consequence is to oversized refrigerating equipment is often installed for a plant. Some of it may not ever run, or if a single piece of equipment runs, it may does do so if inefficiently. There are two ways that this mismatch of estimated load to actual load is addressed. One, rigorous computational methods. Two, rule of thumb adjustment to final estimate determined by judgment. These approaches is to use hour by hour load calculation method similar to the HAP, which is named Hourly Analysis Program, can be used for air conditioning system to take into account each load component by hour and take the total summation and estimate the, the maximum expected load during the day hours and take the total load based on this maximum or worst case scenario which can be happen during this operation in the past when the most calculation were done manually. This procedure was tedious and time consuming and therefore not often used. The advance of computer software can be used to perform such calculation eases the tasks as stated similar to the HAP file which you can be used for AC cooling load calculation. There are another software can be used for estimate the total refrigeration load for larger warehouses and cold stores if it's necessary. However, to have comprehensive operating data for the facility under consideration, so complete and precise information regarding load magnitude and time of occurrence can be input the computer. Ballard describes this procedure. The other method used by experienced engineers due to your experience is to use diversity factor based on the analysis of the load data and understanding of how or more importantly when or how often each load element will occur. The designer will often apply a factor ranging from zero point 0.7 to 0.85, not higher or not less than this range, to calculate the final total load. As a result is the load on which the selection of the equipment is based on during the final design stage and taking the decision and to estimate the final loads of each compressor and evaporators and condenser and condensing unit and refrigerant to be used and the spaces required for the maintenance of this equipment to be installed, which will be according to the final load and according to these outdoor units and indoor units to be installed around the refrigerated space according to the designed layout uh, based on the designer uh, point of view. As can be seen here in two, this slide can present the good arrangement and the bad arrangement of air movement inside. In the left hand side we can find wrong installation for the pallet, uneven air distribution in a store with a unit cooler with a fan circulation. The air couldn't be reached to all products at the same time and some products can be uh, destroyed or damaged from unconditioned or unrefrigerated air can be reached to it. However, in the right side, figure 39 can find fair distribution and even distribution of air, cold air with suspended unit cooler with required space here kept above the. In this slide we can see an example of layout of 2000 meter cube cold store with different dock for trucks to loading and unloading the products, and there are an intermediate corridor to store the different product here, and here the layout, the entrance. This is for passenger car parking, green area, and then here the location for the trucks to be used in this dock or loading area or unloading area to entry this refrigerated space here, and this is for future extension number 2 and number 3 and also future extension for truck parking zone. This is an sample of smaller cold store which may be equipped in hotel or restaurant, small restaurant. One for fruits, one for veggies, one for meats, one for chicken, one for fish. Each about the capacity of each maybe not less than 1 ton, about maximum 2 ton of refrigerated space, and can store beverage, dairy products, veggies, and its compressor range from 1.5 horsepower up to maximum 5 horsepower according to the temperature of freezing or chilling to be used. The doorway can be used, can be, as can be seen here, the insulation material and the lock of the door and the control panel at which monitor to monitor the temperature, inside temperature, and any other data inside, and here a lamp to indicate that there are one person inside or not, to avoid looking or keeping some person inside this cold store. Sure, it has an inside light to facilitate keeping and installing the products inside this small cold store. Here also we can review the installation and two model, or can the model can be considered using CFD applications even for 2D models or 3D models to estimate how the packages can be arranged in rows and columns, and the back wall area and the frontal wall and the ceiling, and where we can using the cooling unit CU or indoor unit, and keep this amount, this space for air movement around the products, and return again from the shelves in between, or the voids in between these columns and rows. To we can here calculate all the temperature and air velocities to ensure the coefficient of heat transfer by convection between the refrigerated air and the product to be refrigerated or stored or kept here inside these cold stores. This also we can see the plan on top view and side view of the arrangement. For 6 meters, 6 meter height, we must keep about from 1 to 1.5 height above the products in the side view, and also we at the end we can keep a space about 1.5 meter, and the pallet should be maximum width about 1 meter, 1.2 meter as a maximum. A 15 centimeter should be kept between the rows to allow the air movement inside and in between these columns and this row. Here this corridor is separates between different cold spaces, and it is equipped with lighting and warning signs for forklifts away from the doorway during opening this sliding door, which reduce the infiltration rather than the hinged, the supported with hinge, supporting with this sliding door is keeping the infiltration load and exfiltration at minimum rate as per the equation listed and studied before. And here is the evaporator or air cooler unit to keep also this corridor, which is wide enough for two forklift, one in two ways, in two directions, go out and go in from the loading dock, maybe this side or another side, and equipped with the indoor to keep this temperature in an intermediate temperature between outdoor temperature and refrigerated space temperature. The thermal properties of different food components based on its protein, fat, carbohydrate, fiber, ashes, the thermal conductivity, and thermal diffusivity, density, specific heat are listed here clearly for each type of food component for temperature between minus 40 degrees Celsius up to 150 degrees Celsius. This table is taken from chapter 8 to indicate some variables or thermophysical properties of the food to be stored, which may help the designer during the design stage and how to estimate the correct product load. Also, these thermal properties models table 2 from chapter 8 gives the thermal properties for different materials, for different substances, especially for water and ice, which most of the products can be transformed or can contain these products as a water for above freezing fruits, fresh fruits and vegetables and dairy products, and for frozen food such as meat, fishes, shrimps, chicken, and frozen fruits or vegetables can be estimate the ice thermal properties instead of the products according to the predetermined percentage of water content inside this food compared to its chemical composition. Continue table 4 for enthalpy of the freezing food at different temperature and the commodity respiration coefficient by Becker at different type of uh, fruits and vegetables such as apple is listed here, F respiration factor, and G this factor is the 2 coefficient which should be used in the respiration load coefficient value for vegetables and fresh fruits and fresh vegetables can be used these two values, which these both tables, table 4 and table 8 from chapter 8 of ASHRAE handbook of refrigeration handbook. Here some typical plan for one story refrigerated facility with truck dock. Here the truck can be parked here, and this is the truck dock which is kept at 5 degree Celsius. However, the outside is maybe 30 degree, 35, 40, 45 as per the city. The width of truck dock here is 15 meter. Also, rail dock here can be equipped for railroad siding if we transport the products by railway. We can use another dock open to the truck dock here, and this is the office area for the operator and the engineers, and this is ramp for the equipment room, and ballast freezer here is a part of the total freezing cold room, and this is the aisles of the products which is separately here by column, grid of columns structure of can be used, and internal walls can be used for different product or different manufacturer or different operators or different rent area can be used for each customer. Maybe one customer rent this area, another customer rent this area, or part of it can be splitted here by the operator, and personal exit here are kept for evacuation for safety code, as safety code should be safety exit at the other side rather than the door opening here. So these designs of larger refrigerated space about 60 meter length and 75 meter width, and in addition to the office area and battery charging area to keep the essential loads, or maybe equipped with generation. This is a typical sectional view of underfloor warming pipes to keep the heat uh, amount here, to add heat if needed for warming from the soil, if freezing from the soil, or uh, from to both direction. We can prevent the heat load to be transmitted from this floor or the refrigerated space to the soil, or from the soil to the refrigerated space, with using these warming pipes. In addition, it can be removed any frost forming in both sides by actuating it in frosting time. And this is here the refrigerated truck and truck dock, and vert sliding dock doors here, and sliding door horizontal vapor retarder here skipped, maybe use here, air curtain to avoid air movement from inside outside during door opening and closing, and different installation for roof with insulation and vapor retarder can be also used. And this cushion closer can be used here to keep this area from storm water and vapor from in to outside the refrigerated space. The stowage factor is a ratio, indicates how many cubic meter for space of 1 metric ton, or cubic feet or space 1 longe of ton, or of particular type of cargo occupies in hold a cargo chip. It's calculated as a ratio of the stowage ratio space required under normal conditions, including the stowage losses caused by means of transportation or packing due to the weight of the cargo. And the stowage ratio can be also chip designed as refrigerated, and evaluate the efficiency of use of the cargo space on the ship. For example, if we have 1 ton of water, so a ton of water, the density of water is 1000 kilogram per meter cube. So 1 ton of water will occupy 1 meter cube as a volume. However, if we have iron, the density of iron makes it that zero point 0.4 meter cube, the 1 ton of iron will occupy only 0.4 meter cube due to its larger density. So we can, for cars it's 4.2, for coal it's 1.4, for grain 1.3, for light crude oil 1.07, for heavy crude oil about the water 0.95%. The 1 ton occupy 0.95% meter cube. So if we have apple, we have to get the stowage ratio, the ton of apple, how much it will be stored in how much meter cube. For if we have meat, we have to check its stowage ratio to get. So its stowage ratio is a function of the water content also of the product, and most of the food have a product has a water content ranged from at least zero point 0.6, zero point 0.7 up to 99% or 100%. So the stowage ratio factor should be considered during the design and the space available for the capacity to be refrigerated and to be stored for certain time. Here also, to continue, the subject which will be described in the previous slide about the stowage ratio, can be find here this explanation. You can check it by yourself. Also, this slide continue how we can arrange the barrel inside cold store for different materials such as cola products, or raw products of cola can be in this barrel, can be stored, such as Coca-Cola and Pepsi company. must have this cold store to store this amount of cola for their production range during a certain period. For widgets, how to install this slide also showing again how can be avoid uneven air distribution in a store with unit cooler to facilitate the air movement and make it fair distribution and to reach all the products installed inside the refrigerated space to keep it fresh, especially for veggies and fruits. Finally, in this slide, we will present a solved example for an cold store, refrigerated cold store under design to estimate the total cooling load required for this room, which is have dimensions of cold store are 6 meter long, 5 meter wide, and 4 meter height. The ambient air is 30 degrees Celsius at 50% relative humidity. However, the internal air is 1 degree Celsius at 95% relative humidity. The wall and roof and floor are insulated with 80 millimeter polyethylene with U value of 0.28 watt per meter square Kelvin. The ground temperature is 10 degrees Celsius. There are 4,000 kilograms of new apple arriving each day at temperature of 5 degrees Celsius and its specific heat of 3.65 kilojoule per kilogram. Estimate 2 people working in the store for 4 hours a day. They will give off around 270 watt of heat per hour inside. If there are 3 lamps at 100 watt each running for 4 hours a day, the same hours of the working persons inside the refrigerated store. In cold room evaporators, in these cold room evaporators, there are using 3 fans rated at 200 watt each and estimate that they will be running for 14 hours per day. It uses an electrical heating element rated at 1.2 kilowatt. It turns for 30 minutes 3 times per day and estimate that 30% of the energy it consumes is just transferred into the cold room only. Estimate also that there will be 5 volume air change per day due to door being opened. The volume is calculated at 120 meter cube. Each cubic meter of new air provides 2 kilojoule per degree Celsius. The air outside is 30 degree Celsius and the air inside is 1 degree Celsius. You are requested to calculate the total cooling load of these cold stores based on this transmission load to be considered upon walls, roof and floors. Use the overall heat transfer coefficient for the selected wall composite wall construction and according to the outside air temperature and the ground temperature as the soil temperature and according to the product load of 4,000 kilogram 4 ton with a certain specific heat and arriving temperature and according to the number of people and number of lighting lamps and the evaporator fans and electrical heating elements percentage to be considered or reflected on the internal loads and according to the air change directly to be taken according to each meter cube based on the total volume of this kilo of this cold store based on 2 kilojoule per degree Celsius difference between inside and outside, where outside the 30 and 1 degree Celsius is kept inside. So you can find the solution of these load components in the next 2 slides as a final or as the end of this lecture. Firstly, we have to estimate the transmission load on each side of the room from side 1 to side 4 and the roof and the floor, and then get the total amount of the wall areas and the roof areas, taking the same temperature difference between inside and outside. Regardless, here we are didn't taking into consideration the facing north or facing south or facing, and treated all the wall as a temperature difference, constant temperature difference for the four sides and the roof, except the floor is kept between the two difference between the ground temperature and the inside air temperature. And finally, we can get the kilowatt hour per day consumed, based on this calculation of transmission load as shown here. The total, you can check all these values by yourself. Then the product load can be considered between the temperature difference between enter and store temperature and specific heat of the arriving apple and the mass of apple, and divided by 3600 to detect this product load per day. Then the internal heat loads components such as people and lighting are listed here, you can check. And then to go to the equipment load, the evaporator fans and infiltration load. And finally, you can estimate the total cooling load based on the summation of these four components: transmission, product, internal and equipment load, and finally the infiltration load. And finally, you can take safety factor of 20% to get the total cooling load of this cold store, which is equal 86.7 kilowatt hour per day. Thanks for watching, and you can find the reference of this lecture at the next two slides, and you can prepare your conceptual design report based on the design problem based on this example and this way. And you may need additional review and additional references to get the most required design criteria during preparing your conceptual design report of the refrigerated cold stores with the specified dimension as listed in that proposal required to complete these course requirements. Thanks for watching. Seeing you inshallah.